Howdy, folks. Well, here we are for part two of thermochemistry, which means exam time is near. Today's lecture should pretty much wrap up the material in chapter 19. Now, this lecture is scheduled to be viewed on Wednesday, April the 8th. So normally then we would have a review on the following Monday, April the 13th. And I think we'll do that. Let's do it by Zoom. We'll have a nice live Q&A, and we'll do it at 5:30, our regular class time. Now, if you don't have Zoom installed, give me a shout and I'll help you with that. But again, if you don't have Zoom or you don't want to do that, we will record the meeting and post it so that you can at least view it. Now, the exam then will be on Wednesday, the 15th, at 5:30. I'll post a link where you can print or view the exam. You'll have a limited amount of time, probably 2 hours, to complete the exam and submit it by photo. And again, take good pictures. Make sure that I can read everything. Include your scratch paper. Now, clearly, we can't keep you from collaborating on this, but we, appreciate if you just keep this as an individual effort. Now, obviously, you have all your class material, everything there available to you, including the internet. So avail yourself of that. If you want to make this open book, if you need to refer to notes, it's not like we're looking over your shoulder. So again, I'll have you complete the entire exam. You won't have the luxury of circling any, I'm afraid. And that's hopefully how the exams are going to work. All right, if you have any questions about that, again, just get a hold of me. Okay, well, just to recap what we talked about in Module 1, we were all over delta H and how to measure it, calorimetry, that sort of idea, and summation of heats of formation. Then we introduced the idea of randomness, that might be a driving force behind reactions that normally wouldn't go. An endothermic reaction you wouldn't think would spontaneously happen, but it turns out, sure, if we can tie that in with a lot of randomness, it may happen spontaneously. So there's a trade-off between the delta H and delta S that ultimately gives you a quantity called the delta G, the Gibbs free energy. Now, all three of these are state functions. It depends on what pressure and what temperature everything is at, which means that if there's a process, there's going to be a change in the delta H or a change in the S and a change in G. Well, with state functions, it turns out if you were to add two reactions together, like in Hess's law, you can add their two delta H's together to get the delta H for the sum of the two reactions. Well, it turns out that state functions are like that. We can do that with delta S's and we can do that with delta G's. Now, this brings up an interesting concept, is coupling reactions. How could we take a reaction that normally would not be spontaneous and couple it with something that is spontaneous so that the two are tied together into one overall reaction? And if we can get one to pay for the other, for instance, then we might get a sum of those two reactions that is spontaneous. It turns out in human biochemistry, this happens all the time. There are a lot of things that go on inside us that are not normally spontaneous, but are coupled to reactions that are, and consequently give a negative delta G, and suddenly we're moving forward. Now, for instance, if we look at how we obtain iron, just solid metallic iron, well, it just doesn't lay around on the ground. It's actually laying on the ground as iron 3 oxide, iron ore, that has a lot of iron oxide in it. Well, this is not a spontaneous reaction for iron ore to just spontaneously give up its oxygen and become iron metal. To reduce the iron from iron plus 3 back to iron 0, that's got a positive delta G, 1487 kilojoules. That's a big uphill battle. But it turns out here's how they do it. They take the iron ore and melt it. This big molten bowl of melted iron oxide. And they begin to bubble carbon monoxide up through it. Now, they make the carbon monoxide by burning coal in the absence of a lot of oxygen, just in a limited amount of oxygen. And it turns out that this makes CO2. Two of them. Actually, let me put a little room there. 2 CO2s. Well, the delta G for this is negative. It's negative 514.4 kilojoules. But, using the carbon monoxide, bubbling it through there to actually help reduce the iron ore back to iron even if we sum these two reactions together, the sum of these two numbers would still not be negative. The negative 514 wasn't enough. But notice something, our stoichiometry isn't right here. If 3 oxygens are created here in this iron oxide reduction, then if I wanted to couple that and use those 3 oxygens as my reactant with the carbon monoxide, that would require that I triple this reaction, meaning I'd need 6 carbon monoxides, I'd need 3 oxygens, and that would make 6 CO2s. That would also triple the negative 514.4. Well, that means then if I sum these two reactions together, canceling out the oxygens, here's the overall reaction. 2 iron oxides will react with 6 carbon monoxides to become 4 irons and 6 CO2s. Sure enough, this thing has a delta G. Now that I've tripled the minus 514, it's got a delta G of minus 56 kilojoules. So as the carbon monoxide bubbles through the iron, the molten iron ore, sure enough, this oxidation reduction reaction begins. And it's because these two reactions have a reactant and a product in common and could be coupled together. Again, you see this over and over and over in human biochemistry. Now, what we'd like to look at next is the relationship between, oh, by the way, there's a homework problem, I think, or I may have put one on the green sheet, where if you have to add reactions together and have to add their delta Gs, again, the rules of Hess's law would still apply. If you reverse a reaction, the sign of delta G changes. If we take the multiple of a reaction, same multiple of delta G. So really the same game as Hess's law. All right, well, what we'd like to look at now is the relationship between the equilibrium constant of a system that might approach an equilibrium and its delta G. I mentioned at the end of the last module that as you approach equilibrium from the reactant side, well, in essence then, the delta G is negative until it reaches equilibrium. And at that point, everything seems to have stopped. Well, at that point, delta G is 0. On the other side of the equilibrium, it's an uphill battle, right? So delta G becomes positive. But in the reverse reaction, delta G would be negative approaching equilibrium from the reactant side. So they sort of meet. The reverse reaction has a negative delta G if we were to start on that side of the street. If we started on the reactant side, that would have a negative delta G also. They would both drop in Gibbs free energy until they reached a minimum. That minimum happens right at equilibrium, and that's where delta G equals 0. We can use that idea to show a mathematical relationship then between the delta G of the reaction and its equilibrium constant K. Okay, well, deriving this mathematical relationship between Gibbs free energy and the equilibrium constant isn't really that big of a trick. As a matter of fact, let's use an equilibrium that we discussed a lot back in our equilibrium chapter, was the production of ammonia, the Haber process. Remember, it takes a nitrogen, 3 hydrogens to make 2 ammonias, and it reaches a decent equilibrium if you have the pressure high and the temperature just right. All right, so if we were to make a graph then of, let's say, the equilibrium where it's 0% complete, meaning on this side it's just nitrogen and hydrogen. On this side of the graph it's 100% complete with just ammonia. And we'll let the y-axis of our graph, so this is 0% done, this would be 100% done. But we know it actually reaches an equilibrium somewhere here in the middle. I kind of alluded to the fact that as you approach equilibrium, the delta G is still negative. And as you approach the equilibrium from this side, the delta G would be negative. At right here, at that instant, at equilibrium, the delta G is actually 0. All right, so we're letting the y-axis actually equal then the Gibbs free energy of formation for compounds. So the sum of the nitrogen and hydrogen's Gibbs free energy is up pretty high. The ammonia is down here. So if it were to go 100% complete, the slope of this line would essentially represent then delta G. Over the entire course of the reaction, that would be the change in G that we would get from the summation law, sum of products minus the reactants. But we know that reactions don't run at a steady speed. We looked at that in our very first kinetics chapter. That when you open the gates, a reaction comes out the gates very fast because there's a lot of reactants banging into each other. But as they get consumed, the reaction rate begins to slow. Well, the same thing happens with delta G. It's not as if the delta G changes steadily over the course of the reaction. It comes out of the gate pretty fast. And as a matter of fact, if we wanted to know, well, what's the instantaneous change in G, let's say right at that point in the reaction, well, that would be represented by a tangent to that line. The slope of that line would be the delta G at that instant. All right, well, it turns out that that has a relationship, a mathematical relationship between what the delta G is here on the south side of equilibrium related to delta G naught, the overall average delta G. Here's the equation. It turns out that delta G instantaneous is equal to delta G naught plus a little bit of an adjustment that has to do with the value of Q, the reaction quotient. Remember, the reaction quotient is where we plug in the current values in the equilibrium expression. Q is where it is, K is where it wants to be. Well, this little adjustment is RT, the ideal gas constant, again in kilojoules, that's the 0.008314, the temperature in Kelvin, and the natural log of Q. All right, so we could find the instantaneous change in G at any point along that reaction. What we need to calculate at that point would be the value of Q. Now, think about this for a second. If Q is a very, very small number, meaning you're way back here at the beginning of the reaction, well, Q is going to be less than 1. It turns out any number less than 1 that you take the natural log of is going to be a negative number. So that means back here at the beginning of the reaction, this is going to be very negative. And if delta G is already negative, which we've established here, that's going to make the slope of the line even more negative. Well, sure it is. If I put a tangent on there, the slope of that line is much more negative than the slope of the overall line. So you can see how the equation works. When Q is small, suddenly the delta G is more and more negative, meaning you haven't reached equilibrium yet. All right, well, that's kind of what we established. Once we reach equilibrium, however, this delta G instantaneous would be the slope of this tangent right at the bottom of the curve. Well, the slope of that tangent is 0. So at equilibrium, where Q is not Q, it's K, the delta G instantaneous is 0. All right, well, let me rearrange or erase this, and we'll rearrange this equation and get us a usable mathematical relationship between K and the delta G. Okay, so the equation we just had on the board, the instantaneous change in G, would be related to the overall change in G that we could determine by using just the Gibbs free energy of formation, products minus reactants. But there's a little adjustment to that delta G that gives us the instantaneous change, and that was related to the value of Q, where you are in terms of in your relationship to the equilibrium. Are you way south of it or way north of it? And that determines whether or not the delta G instantaneous is a negative slope or a positive slope. Okay, well, at equilibrium, however, right at the bottom of that curve is what we're interested in, the relationship between the equilibrium constant and delta G. Well, at equilibrium, we said that Q is not Q, it's K, because you're at equilibrium. And delta G instantaneous, the slope of the tangent to that curve at the very bottom, was 0. Well, if we plug in 0 for that delta G instantaneous, and just put the RT ln of Q on the other side, here's what we get. Delta G naught, this is the overall delta G that we just used the summation of Gibbs free energies, is related to the equilibrium constant of a reaction. And you'll notice the negative sign out in front means that if it's a very large equilibrium constant, it would be a very negative delta G. Well, that kind of makes logical sense. If an equilibrium constant is large, it favors the products. It's probably going to come out of the gate pretty quick and very spontaneously. So a negative delta G would make sense. All right, well, let's plug some numbers in here and just see how this works. Okay, so just to do an example with this relationship between delta G and K, if we were to look at the equilibrium between hydrogen gas and bromine liquid with hydrogen bromide gas, it turns out that at 25 degrees, the delta G for the forward reaction here is negative 107 kilojoules per mole. All right, well, it looks spontaneous then. Can we find the equilibrium constant? Well, we know the relationship, delta G naught, the minus 107, is equal to minus RT ln of K. Well, we know the R constant, and the temperature was given at 25 degrees centigrade, or 298 K. All right, well, let's plug in the numbers. We know that delta G, the negative 107 kilojoules. Oh, I'm going to have to move this over a little bit. This is going to be long. So minus 107 kilojoules is going to be equal to negative R 0.008314 kilojoules per mole K times the temperature, 298 K, times the natural log of the equilibrium constant. All right, well, let's rearrange everything. The ln of K then is going to be the negative 107 kilojoules divided by the negative 0.008314 kilojoules per mole K. Oh, this was kilojoules per mole, so you can see everything cancels out here. And if this was in Kelvin, this would be 298 K. So all the units actually disappear because the natural log of the equilibrium constant is a pure number. It's unitless. All right, well, let's crunch everything that's on this side, because now in order to find K, we're going to have to take an inverse log, take e to whatever this number is. Note that the two negative signs have canceled out. All right, well, let me get my calculator here. Okay, well, the answer comes out 43.1874. Now, I carried some illegal significant figures there. Again, I always do this when I'm going to take an inverse log, because now the K value is going to be e to the 43.1874. Well, this turns out to be approximately 6 times 10 to the 18th power. All right, so it appears, again, that given this very negative delta G, it corresponds with a very large equilibrium constant, which would definitely favor the products. All right, well, let's do another problem. Let's do it the other way around. Suppose we had the value of K, and we wanted to find the delta G for that reaction. Okay, well, let's do one the other way around. I think you'll find this one's actually a little easier. I should have done this one first. If we look back at that complex ion formation stuff that we talked about, right at the end there of chapter 18, one of the examples I used was silver and ammonia to form a very stable complex where the two ammonias attach themselves to that silver ion. It had a formation constant of 1.7 10 to the positive 7th at 25 degrees centigrade. Given that equilibrium constant, could we calculate what the delta G naught for this reaction is going forward, the Gibbs free energy? Now, I'd anticipate a pretty negative value because, again, this looks like it likes to go forward toward products. All right, well, in this case, we're looking for the delta G naught. All we need to do is plug in R, the temperature, and the natural log of that formation constant. All right, well, let me make a little bit of room. All right, well, delta G naught then should equal negative 0.008314 kilojoules per mole K, 298 K, and the ln of 1.7 10 to the positive 7th. All right, looks as if, since that's a pretty large number, this natural log is going to be positive, so this is going to be, with this negative sign out in front, this delta G should be pretty negative. All right, let me crunch some numbers. Somebody back me up out there. I got negative 41.2 kilojoules. Now, again, that would indicate reaction spontaneity, but we kind of anticipated that given that large equilibrium constant. All right, well, so you can kind of see then the relationship between the equilibrium constant and delta G. There's one last little thing we need to tie up here to wrap up our chapter on thermodynamics. All right, well, the thermodynamics here at the end of the chapter kind of explains something that we looked at back in our equilibrium chapter, was that temperature affects equilibrium constants because temperature affects rate constants. But we never really did derive an equation that showed the mathematical relationship between the equilibrium constant and temperature. We did it with rate constants. If you remember, that was the Arrhenius equation. It had that energy of activation business in there. Well, this is very reminiscent of that. As a matter of fact, look at this. If we have delta G is equal to delta H minus T delta S, and now we've established a relationship between delta G and K, that delta G is minus RT ln of K. Well, we could set that equal to delta H minus T delta S. Well, a little algebraic acrobatics here. If we divided both sides by minus RT, suddenly the natural log of the equilibrium constant is equal to negative delta H over RT, because I divided by a negative RT here, and I divided by a negative RT here. All right, well, that's kind of interesting because then the temperatures cancel out at this point. And if I were to separate out the temperature in the denominator and make it look like this, that the natural log of the K is minus delta H over R 1 over T plus the delta S over R that's left over here at the end. This looks very reminiscent of the Arrhenius equation. It had a rate constant here, and this was the E sub A of the reaction. This was the term A, called the frequency factor, the Arrhenius constant. Well, if you recall, we got rid of that Arrhenius constant by taking a two-point approach to this. We said, what if we measured K1 at T1 at some temperature, and then we changed the temperature and measured the K again and subtracted those two equations from one another. All right, well, let me make a little room. You can see kind of where we're headed here. Okay, here it is. This is what we did with the rate constants last time. We said, well, what if we just measured two equilibrium constants for a reaction at two different temperatures? Well, in that case, then the ln of K2 would be delta H over R 1 over T2 plus the delta S over R. Well, K1 would be replaced with T1. If I subtracted equation number 2 from equation number 1, I'd get the ln of K2 minus the ln of K1, which, if you remember, is really the natural log of the quotient of those two equilibrium constants. This turned out, if we factored out the delta H over R and reversed these two terms, the negative sign disappeared. And when we subtracted delta S over R from delta S over R, this became 0 out here at the end. This looks very similar to the Arrhenius equation that related rate constants to their absolute temperatures. The only change was this wasn't the delta H of the reaction. This was the E sub A of the reaction, the energy of activation. All right, well, I think there's one problem that I may have assigned in the homework that does one of these, where they give you, remember there's 5 pieces here. There's the delta H, there's the 2 temperatures, and the 2 Ks. Now these aren't rate constants, these are capital Ks. They're equilibrium constants. But the similarity of this equation to the Arrhenius equation is pretty obvious. So again, we're just going to dust that off and apply it to something a little bit new right here. All right, well, this pretty much signals the end of chapter 19. So let's do a quick review. All righty, well, we started off, here, let me switch sides. We started off this discussion talking a little bit of theoretical about, the state function U, internal energy being equal to heat plus work, that's the way that a change in U manifests itself in one of those two components. And we defined work as expansion work, negative P delta V work. And we talked a little bit about that constant, that 2.48 kilojoules per mole of gas produced in a reaction, that mechanical work equivalent for that. Well, then, after we talked about delta H's and reminded you how we used to measure these Q values by calorimetry or by the summation law of heats of formation or using Hess's law, after we got past that, we introduced entropy, the idea that the other driving force behind a reaction could well not be the delta H, but the delta S. And we said for any spontaneous process that delta S had to be greater than Q over T, the heat change divided by the temperature at which the reaction was happening. And again, that's because of the second law, that the universe, is a positive delta S system. That if you measure any spontaneous process, that sure enough, the delta S is going to have to be greater than the Q over T. Now, we said for an equilibrium process, like a phase change, though, the delta S was equal to Q over T. I did a couple examples of that where we had, I think, water, and then we did one with carbon tetrachloride where we had either the heat of fusion here for the melting or the heat of vaporization here divided by the temperature at which it occurred. And that tells you the change in entropy when, say, something goes from solid to liquid or from liquid to gas. All right, well, let me erase here and we'll put a couple other things on the board. All right, the third law of thermodynamics said that, that the only time the entropy is zero is when something is at absolute zero temperature and it's a perfectly crystalline with no defects compound, then it has no entropy. But once you get off of absolute zero, everything's got a finite positive value for their entropy, which means then that we can sum up, it's a state function, that we can sum up the entropies of our products and subtract the entropies of our reactants to get the delta S. So the summation law worked right here, where you could take the standard free entropies of the products minus the standard free entropies of the reactants. Now remember again that they're given per mole, and so if there's more than 1 mole of a product or more than 1 mole of a reactant, you have to take that stoichiometry into account to find the delta S. Once we had showed you that this was the way that you could actually theoretically calculate a delta S, that led us to our discussion of delta G. And ultimately we got to this equation, that delta G was delta H minus T delta S. And this is the difference between the heat hill and the randomness hill to find that delta G. And again, delta G points to reaction spontaneity. If it's a negative value, the reaction is likely to go spontaneously. If it's positive, it's not. All right, and we also illustrated that there's a summation law for the Gibbs free energy of formation. So you can find delta G a couple ways. Either go the long way, find delta H and delta S, and that'll tell you delta G. But you can also do it if you're at temperatures, other than 25. This would be handy. But if you're doing it at 25 degrees, just do the summation law. The Gibbs free energy of the products minus the sum of the Gibbs free energy of the reactants. So this works for delta H, delta S, delta G, and in the appendix of your book, they've listed all of those. Again, be very careful because the delta S's are given in joules per K, where everybody else is in kilojoules. So don't mix and match. Make sure you've got everybody in the same unit. All right, well, let me double check and make sure we haven't skipped anything here. Okay, we also talked about delta G versus temperature. And we showed you all kinds of scenarios, like what if it was an exothermic reaction where delta H was negative, but it created randomness where delta S was positive? Well, it turned out that the delta G ends up having to be negative. It's going to be spontaneous at all temperatures. So there's all kinds of questions that we can frame around that. I put a couple of them on the green sheet, so you get the idea. For instance, if I told you that something was endothermic and was creating orderliness, I'd want to know then, well, under what conditions might it be spontaneous? Well, at that point, if you look at endothermicity, where delta H is positive and delta S is negative, then delta G can't be anything but positive in that situation, and consequently, there's no temperature under which this thing is going to be spontaneous. You're going to have to really push this thing. All right, so again, there's a lot of questions around that. Delta G versus temperature. All right, well then, once we discussed that, we talked a little bit about the relationship between, well actually more than a little bit, the relationship between delta G and the equilibrium constant. And we started off with this equation, that delta G instantaneous is equal to delta G naught plus RT ln of Q. That's if your conditions other than equilibrium, you can put in the Q value and actually find out what the delta G is at that instant in the course of the reaction. But we use this to approach equilibrium where delta G instantaneous is 0 and Q is equal to K to come up with this equation, that delta G naught is minus RT ln of K. Now this one I like because it's a real easy relationship between the two. If I give you one, you should be able to give me the other. Now at the very end of the chapter, I derived this Arrhenius-like equation that says that the natural log of an equilibrium constant K2 over K1 is equal to the delta H of the reaction divided by R times 1 over T1 in Kelvin minus 1 over T2 in Kelvin. What this does is it relates the equilibrium constant of a reaction to temperature. We never really got a mathematical formula for that, and so here it is. And like I said, I think I may have sneaked one problem in the homework that deals with this. I don't think there was anything on the green sheet, but again, it should look awful familiar. And again, if I give you any 4 of these 5 things, the 2 temperatures, the 2 Ks, or the delta H of the reaction, if I give you any 4, you should be able to come up with the 5th component. All right, well, that's pretty much the review for Chapter 19. Exam time is near. So again, we'll try a little Zoom question and answer on Monday the 13th, followed by our exam on Wednesday the 15th. So anyway, I'll see you at the Zoom meeting on Monday. So long.